Hey everybody, Dr. A here, and in this video we're going to be exploring an example of how to calculate the buckling strength of a built-up steel column. So let's go ahead and get into it. In the given information, we're being told that an A992 W18 by 65 column is 15 feet tall, and we have a KX and KY value of 1.0. So those are our effective length factors 1.0, which indicates that the column is pinned at its ends. There are two 3/8 by 4-inch flange cover plates, and we're being asked to compute the LRFD design compressive strength. So in this little figure we're given here, we see that W18 by 65. I'm going to go ahead and sketch that on there. This is our W18 by 65, and then we see the two 3/8 by 4-inch cover plates. So this is our 4 inches, and then of course this plate thickness right here is 3/8 of an inch, and you see you have one on this flange and you have an identical plate on the other flange. And how would these be attached? Well, in this particular example, it doesn't say, but you could assume that these are probably welded here to these flanges, or they could be very securely bolted through these flanges. But again, we're not really concerned with that for the sake of this example problem, okay? So as we dive into the solution, we're going to be referencing the AISC Steel Construction Manual 16th edition. So I'm going to scroll over to the next page, and I'm going to go ahead and write solution here. And I'm going to say we're going to reference the AISC Steel Construction Manual. I'm abbreviating that SCM 16th edition along the way. Okay, so the first thing that I say we need to make note of is which buckling limit state is going to control for this column, for this kind of configuration. Well, we're going to make a note here. We're going to say flexural buckling controls. Okay, now if you remember, when we deal with column buckling of steel sections, there are three typical limit states that we need to keep in mind. One of them is flexural buckling. The second one is torsional buckling. And the third is flexural torsional buckling. So if you remember from your background information on steel column design, flexural buckling could occur with any kind of column cross-section or configuration. Torsional buckling, one of the other limit states, occurs when you have doubly symmetrical cross-sections with thin elements, so the cross-section will tend to twist. And then the third limit state, flexural torsional buckling, so that's flexural with a hyphen and then the word torsional buckling, occurs when you have unsymmetric cross-sections that tend to both bend and twist. So clearly here we have a symmetrical cross-section, this W shape with the two cover plates. So the limit state of flexural buckling is going to control, okay? The next thing we want to make note of is the cross-section properties, okay, of the W shape. So I'm going to say from table 1-1 of the Steel Construction Manual, we're going to have the information about the W18 by 65, and it's good to just go ahead and write this information down for us to use. So its cross-section area is 19.1 square inches. Its total depth is 18.4 inches. Its moment of inertia about its centroidal x-axis is 1,070 inches to the fourth, and its moment of inertia about the centroidal y-axis is 54.8 inches to the fourth. Okay, so that's the information about that W18 by 65. And again, you can find this in table 1-1 of the Steel Construction Manual. All right. So what do we do? How do we go about tackling this kind of problem to calculate that design compressive strength? Well, what we need to do is follow Chapter E in the Steel Construction Manual. Okay, so what we're going to do is follow Chapter E of Steel Construction Manual. All right, and so ultimately what Chapter E says is phi PN or phi CPN is equal to 0.9 capital FN times A gross, okay? And so A gross is the total cross-section area of our column. Fn is the nominal compressive stress of the column cross-section, and then 0.9 is our resistance factor, okay? And so this is a built-up column, so we have to do these manual calculations, right? So what we're going to do is we're going to compute Ix and Iy for the built up section. And then we're going to take I minimum is the least or the minimum of those two values, Ix or Iy, of that built up cross section. And then what we're going to do is compute R minimum from that, and we get R minimum by saying the square root of I minimum divided by the gross area of the entire cross section AG, okay, and square rooting I min over AG. And then what we're going to do is compute Euler's buckling stress Fe and then the nominal buckling stress Fn, okay? And then once we have this Fn, we go back to this phi CPN relationship from Chapter E, and we have the compressive strength there, okay? So let's go ahead and do this systematically. I'm going to turn the page again, and what I'm going to do is I'm just going to quickly sketch out that cross-section one more time to help us visualize what's going on here. All right, and now I'm going to sketch this pretty quickly, so my artwork is not going to be the most beautiful here. So please forgive me. There's the web, bottom flange, and then there's that second plate, okay? All right. So here we go. Now, this total depth of the cross section is shown here. That is that 18.4 inches, okay? And then we have the thickness of each of these plates is 0.375 inches. 0.375 inches, okay? And so if we establish kind of a reference axis, or we sometimes call it a datum, along this bottom surface, we can call this the datum, and then, we can have a vertical datum here as well, right down the middle of the cross section, okay? And so by doing this, we can clearly see that Y bar, which is the location of the centroid of this entire cross section, is just 18.4 plus 0.375 plus 0.375 divided by 2, all right? And so we can quickly get that Y bar is 9.575 inches measured from that datum, that bottom datum right here, okay? So there's that Y bar, 9.575 inches, okay? Just halfway up the total depth of that entire built up section, okay? Now, the next thing we need to do is calculate that moment of inertia about each cross-section axes, okay? Each of the cross-section axes. So here's what we're going to remind ourselves of. We can say I sub x is the summation of I sub x sub I plus A sub I d sub y sub I squared. Now, this comes from statics. This is an application of the parallel axis theorem, okay? So if you're a little rusty on calculating moment of inertia values of built-up sections, take a look at my statics playlist. I have lots of examples of us doing it there. So let's go ahead and calculate I sub x for this entire built-up section. So this is going to include, the I shape here and both of these cover plates, all right? So for the I shape or the W shape, we have 1,070 inches to the fourth, okay? Now for the two cover plates, we're going to say plus, and then I'm going to wrap this equation around here. I'm going to say 2 times BH cubed over 12, so that's 4 inches times 0.375 inches squared, cubed over 12, plus AD squared for each of the plates. So the area of each plate is 1.5 square inches, and then that D value, D sub Y value, is 9.388 inches, and we're squaring that value, okay? Now, where did I get these values from? How did I come up with these? Well, first of all, that 4 inches, that's the base dimension of each of the plates. So we see that 4 inches here, okay? Now, if you take 4 times 0.375, which is 3/8 of an inch, you get that area of each plate. That's the 1.5 square inches. Now, what about this 9.388? Okay, what is that? Well, this is this D sub Y value, and then I'm going to square it. But how do I get this D sub Y value? Okay, well, remember what we do, and this goes back to statics, okay? That D sub Y value is the distance from the centroid of the part you're interested in to the centroid of the entire shape, okay? So one more time, D sub Y is the distance from the centroid of the part you're interested in to the centroid of the entire cross section. So this is D sub Y, okay? And that is the 9.388 inches. And remember, this is symmetrical about this neutral axis, okay? So what's happening here is you have this occurring for the bottom plate and the top plate. That's why we multiply by 2 out here. So you're really saying 2 times 2 for each of these plates, 2 times BH cubed over 12 plus AD squared, okay? And so when you crank this all through in your calculator, and I encourage you to pause the video and do it yourself, you should get an IX equal to 1,335 inches to the fourth, okay? Now, are we done? Well, no, we need to get IY, and we need to take the smaller of the two, okay? Well, if you recall, we got IY of just the W18 by 65. You saw that that's 54.8 inches to the fourth, way smaller than 1,070. So probably that's going to be the direction that still controls. But let's go ahead and do that work as well. So I'm going to come over here and I'm going to say, similarly, IY is going to be equal to the summation of I sub Y sub I plus A sub I D sub X sub I squared. That's, again, an application of the parallel axis theorem, okay? And I can substitute my values in. I say IY equals 54.8 inches to the fourth plus 2 times BH cubed over 12, but in this case, the base is 0.375 inches, and the H that I'm cubing is the 4 inches cubed over 12, okay? And so here, because we're finding the moment of inertia in the other direction, you're saying this smaller dimension is the base. In fact, in some courses in statics and mechatronics, they call this HB cubed over 12. So you're taking this 0.375 and then you're saying times 4 inches cubed over 12. Now, what happened to the AD squared here? Well, if we treat this this vertical datum through the center line of this entire cross section, then and we see this is symmetrical, then the D sub x values are all 0. You notice that the centroids of all three of these parts here, the two plates and the W shape, lie all along this vertical axis, which means D sub x is 0. And again, I've got some videos in my statics playlist that review just that concept if you need a refresher on that. So I punch this through, and I'm going to get IY is 58.8 inches to the fourth power. And we see that since this is less than IX, we're going to say IY controls, okay? Now what we can do is get the total gross area. So I'm going to say, call that A gross, all right? And we're going to say that that's 19.1 inches squared plus 2 times 1.5 inches squared. And we get this total cross-section area is 22.1 square inches. Now, one more time, where's this 19.1 from? That's the area of just the W18. We got that from table 1-1 of the Steel Construction Manual. And then this 1.5 square inches, that's the area of a plate, and we multiply times 2 because we have 2 plates, all right? And now what we can do is say R sub y is the square root of IY over A gross, and we substitute those values in. You should get a value of 1.631 inches for that radius of gyration. Now, why do I care about that? Why do I need that? Well, if we're referencing Chapter 3 of the Steel Construction Manual and we're following these design equations, we need to get the slenderness ratio, all right? So we're going to say next thing is slenderness ratio, and we often call this KL over R, and of course we're looking at you know, the Y direction, buckling about the Y axis. So this is KL over R Y, and we knew that K was 1 from the given information. The length is 15 feet. We're going to convert that to inches by saying 12 inches over 1 foot. And then we're going to divide that by that RY we just calculated, 1.631 inches. And we'll get a slenderness ratio of 110.4, okay? Now what we do, and again, we're referencing Chapter 3 of the Steel Construction Manual, we calculate Euler's stress, all right? So we're going to say Fe is pi squared E over KL over RY squared. So, of course, that's pi squared times 29,000 KSI divided by that 110.4 that we just calculated, but we're squaring it. And so we'll crank this through and get a value of 23.48 KSI for Euler's stress. And again, from the Steel Construction Manual, this is equation E3-4. Now we can figure out which Fn equation we need to use. So I'm going to calculate this ratio, Fy over Fe. And so A992 has an Fy of 50 KSI divided by 23.48 KSI. And you should get a value of about 2.13, which is less than 2.25, which means that we use this nominal stress value Fn of 0.658 raised to the Fy over Fe all times Fy. And from the Steel Construction Manual, this is equation E3-2, all right? And so we can substitute in values into this Fn equation right here. And I encourage you to punch this along with me. Make sure you get the same thing I'm getting. But I get an Fn of 20.51 KSI. So are we done? Almost done. So finally, we're going to substitute into our strength equation, Phi CPN, and we're going to get that as, of course, that was 0.9 Fn AG, and so that's going to be 0.9 times that 20.51 KSI that we just determined times 22.1 square inches. And so I get a value of about 408 kips, okay? And this comes from equation E3-1 of the Steel Construction Manual, but of course with that resistance factor, that phi factor of 0.9. So what's my final answer? My final answer is this 408 kips. So what that means is that is our design compressive strength using LRFD, 408 kips of this built up column section. Okay, so that concludes this video. If you found this helpful, please hit like and subscribe and be on the lookout for other content like this. Thanks again for watching.